for joining us. We are the NOWJ team, and we are delighted to welcome you to our presentation at BioCreative IX. Today, we will discussing our dedicated work in the ToxHabits Shared Task titled An Ensemble Deep Learning Approach for Detecting Substantive and Contextual Information in Clinical Texts. I'm Kenneth, together with my colleague, and I'm here representing our work from the University of Engineering and Technology, Vietnam National University. We are very excited to share our findings on what we believe is a crucial topic in clinical natural language processing. Here's a quick overview of what we will cover today. Uh, we will start with an introduction, setting the context and outlining our objective. Then we will dive into our methodology, where we will detail the system, architecture, and the various training strategies that we employ. Following that, we will represent our experiment and discuss the key results. Finally, we will wrap up with a conclusion, summarizing our contribution and outlining future directions. Okay, uh, let's start with introduction. In healthcare, extracting crucial information from unstructured electronic health records is vital. Specifically, precise extraction of toxic substance information as expressed in the ToxHabits Shared Task is crucial for enhancing patient care, clinical research, and public health surveillance. The main challenge we face here lies in the inherent complexity of clinical texts. They are often unstructured, contain nuanced language, can be quite difficult to process automatically. To tackle this, the ToxHabits Shared Task specifically focus on identifying and characterizing substance triggers and their contextual arguments within Spanish clinical notes. Our contribution is a novel multi-output ensemble deep learning system. The system is uniquely designed for simultaneous recognition of both triggers and arguments as ToxNER and ToxUse. We carefully leverage diverse training strategies to enhance both performance and robustness of our system, particularly in this challenging domain-specific and low-resource setting. Moving on to the ToxHabit dataset itself. The dataset is a collection of 1,499 Spanish clinical case reports, which have been annotated for each instance of substance and their specific characteristics. The annotation categorizes trigger types into four main categories: tobacco, cannabis, alcohol, and drugs. Alongside these, argument types capture 6 contextual details: type, method, amount, frequency, duration, and history. To give you a clearer picture, let's look at an example from the corpus. Consider this Spanish sentence translated into English. The patient manifests using inhaled heroin 8 days earlier. Here, heroin is annotated as a drug trigger with an inhale identified as a method argument, 8 days earlier as a history argument. So, let's move on to our methodology. Here, we present the overall structure of our multi-output BERT CRF ensemble system. As you can see, it is designed as a multi-stage neural network to effectively identify both triggers and arguments simultaneously. The system comprises 3 main sequential components. First, we have a pre-processing phase, which include crucial steps: document segmentation, sentence filtering, and tokenization. Next is a multi-output BERT CRF modeling, where we generate contextual embeddings and perform sequence labeling for both tasks. Finally, the post-processing phase handles the tokenization, normalization, and ensemble aggregation to generate our final predictions. Let's break down the pre-processing phase further. First, In the sentence segmentation, the input clinical documents are broken down to individual sentences. This is a crucial initial step that helps reduce the computational burden for subsequent stages. Next is the sentence filtering, a binary birth-based classifier then processes these segmented sentences. This classifier, which uses the same BETO backbone as our main model, was independently trained to determine whether each sentence contains at least one relevant trigger or argument. Essentially, it filters out irrelevant content, allowing us to focus on processing only on informative samples. Finally, tokenization. The filtered sentences are then tokenized using the BETO model. This prepares the text for our sequence labeling task, where each token will be independently labeled for both trigger and argument detection using a BIO tagging scheme. The core of our architecture is the multi-output sequence labeling with BERT-CRF. Our core architecture is built upon a shared BETO encoder, which feeds into task-specific decoding branch for both trigger and argument detection. This allows joint learning between the two tasks. The process involves three main steps. First, a shared encoder transforms the input tokenized sentence into rich contextual embeddings. These embeddings are then passed into task-specific emission layers, which project them into per token BIO label scores for each task, trigger, and argument. Lastly, a conditional random field layer is used. This is a crucial step that ensures that we decode the most likely label sequence using the Viterbi algorithm, enforcing global optimality and valid BIO structured outputs, which is vital for maintaining the integrity of our extracted entities. Let's move on to the post-processing. Following the BERT-CRF decoding, we move to the post-processing phase. This critical step refines our prediction and aggregates results. First, the prediction generation at the subword level by the BERT-CRF model are reassembled and normalized into word level spans. This ensures that our extracted entity are coherent and correctly aligned with the original clinical text. To significantly enhance the robustness and reliability of our system, we aggregate outputs from multiple BERT-CRF models. These models are trained using various strategies, as we will demonstrate later. The final output of both trigger and arguments is derived through a majority voting mechanism across this ensemble. This approach has proven to significantly improve overall precision and noticeably reduce prediction variance, leading to more stable and accurate results. To enhance our model generalization and address class imbalance, we leverage three complementary training strategies in our example. Our joint loss function is a simple sum of negative log likelihoods from the both trigger detection and argument extraction CRF layers. We initially set the weights for both tasks alpha and beta to 1, ensuring equal emphasis during training. For increased data diversity, we utilize two main training datasets, a partial and a full dataset, and split it into multiple parts for cross-validation. This procedure results in a set of distinct models trained on different subsets. For individual model training, we experiment with three key strategies. The first one is label-weighted loss. Here we assign higher weights to underrepresented class in the loss function to mitigate class imbalance during optimization. And second, data oversampling. This involves increasing the number of training instances containing trigger or arguments by duplicating such sentence in the training data. if this will effectively balancing the class distribution. Finally, we utilize weighted random sampling to increase the sampling probability of sentence containing trigger or arguments, ensuring that the model was exposed to more informative sample during each training epoch. Now let's move on to the experiment section and see how we built our ensembles. Let's outline our experimental setting. In our core model architecture is a BETO-based coupled with a conditional random field or CRF layer for sequence labeling. BETO, as mentioned earlier, is a powerful BERT model trained on a large Spanish corpus, making it particularly effective at capturing Spanish-specific linguistic nuance of our task. All implementations we built using the Hugging Face Transformer library with PyTorch, and our experiments are accelerated using two NVIDIA Tesla T4 GPUs. For fine-tuning the main BERT CRF model, it took about 1 hour for fine-tuning. Separately, our binary BERT-based classifier used for sentence filtering were trained independently. The total training time for this model was accounted for as approximately 2.5 hours. To maximize the robustness across various scenarios, we utilize two distinct ensemble configurations. For the full training dataset evaluation, our ensemble consists of 6 models. These were primarily trained using a weighted random sampling strategy on data derived from a 5-fold cross-validation split. This means 5 models were trained on 80% subset of the data, and one crucial model was trained on the entire 100% full dataset. For the partial training dataset evaluation, we construct a much larger ensemble of 19 models. These models leverage even more diverse data samples and combine all 3 training strategies we discussed earlier. 6 models using label weighted loss, specifically 5 on 80% resampled data and 1 on full partial dataset. 12 models employ weighted random sampling, 10 on 80% resampled data, and 2 on full partial dataset from 2 separate runs. And finally, 2 models were trained with data oversampling, one with specific class ratio of 9322 for drug, alcohol, tobacco, and cannabis, and another with a uniform 1111 distribution across these categories. This comprehensive ensemble approach allowed us to capture a wide range of model behaviors, significantly enhancing our overall prediction accuracy and stability. Now, let's examine the experimental results for both subtask 1 trigger detection and the second subtask argument detection. Here are the official results for subtask 1 trigger detection or ToxNER. As you can see from the table, our top performing run was the BERT ensemble with sentence filtering and hyperparameter tuning on full trained dataset, which hit an F1 score of 94% and an impressive precision of 97%. It is worth noting that BERT ensemble with sentence filtering on full train also achieved a 94% F1 score, but slightly lower precision at 94%. Moving on to our subtask. Moving on to the subtask 2, argument detection or ToxUse. We apply the same multi-output modeling architecture for configuration design for this subtask. The highest F1 score of 91% for argument detection was achieved by the BERT ensemble on full train model. Interestingly, the BERT ensemble with sentence filtering and hyperparameter tuning on full train dataset model record the highest precision at 95%, while the sentence filtering generally increased precision for argument detection. It did lead to a slight decrease in recall, resulting a marginal F1 score reduction compared to the base full train model. Let's now discuss our key findings and observations from this research. Our multi-output architecture proved to be highly effective. It allowed the model to learn shared representations and capture dependency between both trigger and argument detection tasks, significantly enhancing overall performance by leveraging contextual information from both. Regarding the join loss function, we initially set the alpha and beta weight to 1 for simplicity and to ensure equal emphasis on both tasks. However, for future work, we recognize that adjusting the weights could be a valuable avenue to address potential imbalance in trigger and argument frequency if needed. The ensemble method substantially boosts our system robustness and generalization capabilities by strategically combining diverse models trained with various strategies. The sentence filtering method consistently improves precision and F1 score across most configurations, clearly demonstrating its efficiency in focusing the model on the most relevant sentences. Finally, for future work, while our current system does not incorporate large language models, we plan to explore more on them for richer context understanding and improved performance in complex clinical NLP tasks. Right. To conclude, we introduce a multi-output ensemble system specifically designed for the simultaneous detection of both trigger, ToxNER, and argument ToxUse in clinical text. Our multi-stage methodology effectively combined with initial sentence filtering with a robust multi-output BERT CRF core and an innovative ensemble inference strategy. When evaluated on the official ToxHabits Shared Task, our approach demonstrates competitive performance, achieving strong F1 score and high precision for both subtasks. We sincerely believe that our method and the valuable experience gained from this work will prove to be highly valuable for future participants and researchers in the critical and evolving field of clinical information extraction. Thank you for your attention, and we welcome your questions and feedback.